Hello guys. Today we are going to go over chapter 1 in the Stars, Constellations and Life Cycle iBook. This is chapter 1 on the sun. So as we learned before you guys left the school, our sun is massive. If you recall, when we did our solar system to scale project, the Earth was about the size of a nickel compared to a sun that was 2 meters in diameter. And here's just another comparison. They show a basketball here, a regular sized basketball, and we would be this tiny little dot, about a pencil point, compared to a basketball. And in fact, if you take all of the planets, even the gas giants, and add them all together, they only account for 0.2% of the total mass of the solar system. The other 99.8% is made up from the sun. The sun has layers, just like Earth has layers. We are used to a model of the Earth that has a core, mantle, and crust. Same kind of deal with the sun, except the sun is not made of any solids. It's made of gases. And in fact, those gases are so condensed and pulled together so much that it forms what's called a plasma, which is just a superheated gas that has an electrical charge. The two main gases, or the two main components of the sun, are hydrogen and then helium. Hydrogen makes up the bulk of the sun, and then helium is like 8% of it, and then there's another 1 or 2% that are other gases, but the bulk is hydrogen and helium. There's 6 layers to the sun. We're only going to really concentrate on a couple of them. The core is where the nuclear reactor is. That's where the sun is making all the energy. It's so hot inside the core, about 15 million degrees Celsius, that hydrogen actually gets fused together. 2 hydrogen atoms get fused together and they create a helium atom. And that reaction gives off a lot of energy. That's where we get our sun's energy. From there, this energy moves through 2 more layers. The radiative zone, which is, as the name implies, the light particles radiate out from the core through the radiative zone into the next zone, which is the convection zone. It takes a really long time for photons, light particles, to move from the bottom of the radiative zone all the way up to the convection zone, like tens of millions of years, up to 100 million years. So realistically, we've talked about how it takes 8 minutes for a light particle to go from the sun to our eye. Realistically, that light particle was made or emitted from the core millions and millions of years ago, and it just took 8 minutes to reach the outer layers of the sun to our eye. Next zone is the convection zone, and as this name implies, there is movement of particles rising up to the surface and cooling and sinking back down and getting heated and continuing to circulate. Okay, so these are the 3 inner layers of the sun. We're kind of focusing on where the sun's energy is made, and that is in the core. And it's the same for all stars. All stars that you see in the sky have these layers, and all stars have a core where the energy is made. Then we get to the sun's atmosphere, or the outer layers of the sun. The photosphere is actually the part that you see. When you look up at the sky and you see the yellow disk, that's what you're seeing. You can't see these other layers, like the corona, unless there is a solar eclipse and the moon moves over the sun completely, and then you can see some of that solar atmosphere undulating out into space. It's a really, really cool thing. Other features of the sun include sunspots and solar flares. Sunspots are just regions of the sun that are darker and a little bit cooler. They occur in an 11-year cycle. So every 11 years there's a maximum of sunspots, and then every 5.5 years it goes down to a minimum. Another 5.5 years it's at its maximum. So from maximum to maximum it's 11 years. Minimum to minimum it's 11 years. Scientists actually wondered if that occurrence of sunspots had anything to do with climate change here on Earth. If these spots are cooler, darker areas, then every 11 years shouldn't we see a decrease in heat here on Earth? And they proved that wrong. the sun gives out so much energy that the amount of sunspots on the surface at any given time does not affect climate here on Earth. Every once in a while, solar flares will come out of these dots on the sun, and they'll actually break. They make an arc and they break and they explode out into space. And those explosions can cause all kinds of havoc, damage to spacecraft, danger to astronauts in space. It can wipe out cell communication here on Earth. And there's a lot unknown here. Astronauts are actually studying the effect that solar flares have on communication here on Earth and the effect of solar wind, which brings me to some of the space exploration or space probes that we are sending up right now. The one that we have in space right now is called the Parker Solar Probe. And it is right now up studying solar wind and studying how the corona is heated, that outer layer of the sun's atmosphere. So if we look right in here, it was launched in 2018 in August, and it's still up there right now. Right at this moment, it is at the perihelion, which is the farthest place from the sun. It's right here in between the orbits of Earth and Venus. And it's looping around. It'll make 11 loops before it ends its mission in a quite fiery way. But this website, if you're interested in learning more, has lots of the objectives of the mission. So check this out if you'd like. I'll go back to the lecture here.